We're going to start by taking a look at sequences. And to put it real simply, a sequence is just simply a list of numbers. So notational things for us to think about when we're looking at sequences. We tend to number the elements of the sequence, right? So the first one, the second one, the third one. And so this A1, A2, A3 would be taking the place of, particular numbers that are in a sequence. So let's just make this real simple. Let's say that my sequence is the set of all whole numbers. Okay, well, whole numbers start with 0, so that'd be my first. Then 1, that's my second. Then 2, that's my third. And then we know whole numbers go on as long as I need them to. All right, so that's what this notation means. We always use curly brackets to indicate that we're talking about a sequence. Now, if I can boil my sequence down to a formula, then what I'm going to do is put that formula inside of those curly brackets. Okay, so this a sub n here is just this formula that you see here in example 1, the n plus 5 over n, right? It's a formula telling me how to get each element of my sequence. So that's what I put in the curly brackets. And then often, but not always, you'll see what n value the sequence starts with. And so the default is to start it at 1 and then go 2, 3, 4, all the way up. And when we're talking about an infinite sequence, we'll talk about infinity. So that's the default. And so if you ever see a sequence where they don't bother to write anything, then you can assume it goes from n equals 1 up to infinity. All right, so let's take a look at an example here. So they've given us a formula. They're saying we're starting at 1 and then counting up from there. So let's just write out the first 4 terms of this sequence. So I'm putting a 1 in because I'm starting at n equals 1 for n. I'm then going to put a 2 in for n, 3, and a 4. And of course, I'm not really stopping here, right? I know that it goes on, so I'll put these ellipses here just to indicate to whoever's seeing this that this is in fact an infinite sequence that continues on with this pattern. But of course I can clean up this sequence, right? I can say that's 6, this is 7 halves, this is 8 thirds, and this is 9 fourths. All right, then in example 2, just to kind of change this up a little bit, same look here, except I've stuck an extra factor on top, right? So negative 1 to the n. So when I'm writing out the terms of the sequence here, I know that raising negative 1 to a power isn't going to change the absolute value, but it could change the sign, right? So I'm definitely going to have 6 be the absolute value of my first term, but now I have to think about what happens when I put a 1 in for n for this factor of negative 1. Well, we know that, sorry, I meant to put a 1 here. When I take negative 1 to the first power, I know that that's negative 1. And so what that means is that, yes, I'm still getting 6 from this part, but I'm getting a negative 6 because I'm multiplying by negative 1. But then, of course, when I get to the second term there, where n is 2, I'm doing negative 1 to the second, which is negative 1 times itself, which is 1. So I'm back to a positive number in the second term, right? And then we know the pattern here is anytime we have an odd exponent, we get a negative, and anytime we have an even exponent, we end up with a positive. And so we end up with this sequence that alternates back and forth between negative and positive, but the absolute values of that sequence are the same as our previous example. All right, let's do kind of one that's a little more complicated, just to show that we can put more complicated functions inside of here. All right, so this one is taking the cotangent of n pi over n minus 1. So let's go ahead and list out some of these terms. And notice this one is not starting at 1, so don't go on autopilot too much, right? Always observe what is the n we're starting with. So our first term here is going to be the cotangent of 3 pi over 3 minus 1, the cotangent of 4 pi over 4 minus 1, and the cotangent of 5 pi over 5 minus 1. And then it's going to go on from there. Okay, so let's try to make some sense out of this, right? So that's, of course, just the cotangent of 3 pi over 2, cotangent of 4 pi over 3, and hopefully you're remembering your trig at least well enough to remember that these three values inside the argument of this cotangent function are special values on the unit circle, right? So we can actually figure these out exactly. So remember, of course, that our cotangent of theta is the cosine of theta over the sine of theta. And to me, the best thing to always go back to when it comes to quickly trying to recall special values on the unit circle, I kind of said it before I meant to there. The best way to recall values of sine and cosine are to think about values on the unit circle at these special angles. All right. So let me just try to change the color of my pen here. So let's think about where these angles are, right? So 3 pi over 2, right? That's all the way down here, right? That's where we're going to find 3 pi over 2. 4 pi over 3, right? So that's a full pi plus another third pi. So there's your 4 pi over 3. And then 5 pi over 4 is right there. All right, so let's see how well we remember this. Okay, so what's happening here is that my cosine, right, is 0, and my sine is -1. So as I write out this first term, this would be 0 over -1. Here, this is where the cosine is negative but small, and the sine is also negative but large. So that's going to be -1/2 for the cosine and negative square root of 3 over 2 for the sine. And then this one, remember, anytime you're dividing by 4, that's where the sine and cosine are the same. And so that's going to be -√2 over 2, -√2 over 2. And we can do a little bit of cleanup work here, right? So of course that's 0. This I multiply by the reciprocal, and I end up with 1 over √3. And then here, of course, I get 1. And it goes on from there. All right. So that's just a couple examples of us writing out some of the terms of sequences that we're given. Now, what we're going to probably spend most of our energy on when it comes to sequences is figuring out what happens to them in the long run. So I'm going to be introducing to you a lot of principles, a lot of rules, a lot of theorems, but to kind of hopefully reduce how overwhelmed we get with all of the things that I present here, here's what I want to say at the outset. Pretty much every idea I'm giving here, you have already learned. You've learned it back in Calculus 1 when you were dealing with functions, okay? So you'll notice that in this first definition here, it says a sequence has a limit, L, that we write this way, if we can make the terms as close to L as we like by making n sufficiently large. Okay? So in other words, we're just saying in the long run, what happens to this sequence? Does it settle down to a number? And if it does settle down to a number, that's when we say it converges or is convergent. And then if it can't settle itself down to a number, it diverges. Okay? So see this, we're talking about limits, right? You worked extensively with limits back in Calculus 1. And so what hopefully you kind of view this first section as is kind of just a refresher course in some of your techniques for calculating limits that you learned back in Calc 1. So example 4 says determine if this sequence converges or diverges. Well, how about we check to see if this thing has a limit as n goes to infinity. And so what I'm going to first do is just write the expression. Okay. And let's think about how we might manipulate this. Okay. The whole idea is how can I tell what this is settling down to, if anything? And one of the principles that I would remind you of here is just taking a look at this. When we're looking at +5, but you make n really large, the 5 really isn't all that significant, right? So like if n is 1,000,000, who cares about 5, right? So if you're going to give me $1,000,000 and versus $1,000,000, $1,005, I'm just not going to really care, right? So we kind of have the sense that this 5 really doesn't matter, and so we kind of end up with this idea of n over n is 1, and so I'm kind of thinking the limit is 1. Okay, but to do that more formally, here's what we're going to do. Anytime we are dividing multiple terms by just one single term, I can always break it up, right? I can say that this is the same as that, which of course turns into 1 plus 5 over n. But here's the thing we do know. Anytime you have a number divided by n, as n gets large, 5 over n, right? As n goes to infinity, 5 over n has to go to 0, right? 5 divided by a big number is close to 0. So this ends up just equaling 1. So we can say that the sequence converges to 1. All right, well, good. So let's take a look at example 5. Okay, so we want to determine if this sequence converges or diverges. Okay, well, we know what happens when we don't have the -1 in there. Okay, so what I would suggest is to think about, okay, what does it mean for this sequence to converge to 1, right? Well, for that sequence to converge to 1, after a while, you start to get things like this. You start to get, dot, 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 something that's close to 1, something that's close to 1, something that's close to 1, right? That's the idea of this thing converging to 1. So I guess I should point down here to make it clear I'm talking about this sequence, okay? Sorry, I'm trying to change my pen color and it's giving me trouble there. All right, so let me change colors here. So now to make it clear, I'm talking about this one now. Okay, so if that's the case, then this one should behave in the same sort of way, right? But what's going to happen is you'll get something close to 1, but then you'll get something close to -1, and then something close to 1, and then something close to -1. So am I able, in a case like this, to say that my sequence is settling down to a particular thing? The answer is no, right? Because it keeps alternating between things close to 1 and close to -1. Now, this alternating sequence might have been okay if this thing was settling to 0, right? If I was going a little bit above 0, a little bit below 0, a little bit above, a little bit below 0, then we could think that that's probably going to settle down to 0 eventually. But since this settled down to something other than 0, okay, then it is not going to be convergent. So we'll say it's divergent, right? Divergent because the limit of the absolute values, right, as n goes to infinity, is not 0, and the sequence is alternating. So something we can kind of hang our hat on here is that if our sequence is alternating, the only way you're going to get a convergent sequence is if the absolute values go to 0. All right, now let's revisit example 6 here. Okay, so we wrote out the first couple terms of it, right? So remember, we figured those out. 0, 1 over square root of 3, 1. Kind of looks like maybe things are getting bigger as I go, so that doesn't necessarily give us a good feeling about it being convergent, but let's see what we can do with it. So what we need to do is take the limit and see if that limit actually exists. So we'll take the limit as n goes to infinity of the cotangent of n pi over n minus 1. Now, what might be worth doing here is to figure out what happens just to this expression, right? Let's just focus on that. So over on the side here, change my color. Let's figure this out. Limit as n goes to infinity of n pi over n minus 1. So I want to take this opportunity to remind you of a particular technique for finding limits like this. Again, you might get the sense that this minus 1 really doesn't mean a whole lot, right? In the long run, when n gets big, who cares about minus 1? And so if that minus 1 was gone, then the n's would cancel and you'd be just left with pi. So our intuition tells us that the limit of this expression probably should be pi. Right? But again, how do we show it? Well, what you can always do, again, I'm going to switch my colors, but there we go. What we can always do is we can take the top and the bottom of a big fraction and multiply it by whatever we want. So if I multiply by 1 over n in this case, then what's going to happen is as I distribute through the bottom, I'm going to get rid of this n, and then I'm going to have a 1 over n. But having a 1 over n is actually really nice because a 1 over n, we know what happens to that as n gets big, right? It goes to 0. So what we're left here with is these guys canceling, so I just have a pi on top. 1 over n times n is 1 minus 1 over n. But as n goes to infinity, this guy goes to 0, right? So in fact, this does equal pi. So I know that in the long run, what's going to happen to my actual problem here is that this is going to equal the cotangent of pi, right? But what is the cotangent of pi, right? It's the cosine of pi over the sine of pi. But where is pi on the unit circle, right? It's way over here, right? And we remember from our trig that the sine function is the y value on the unit circle. So that means, what do we have? We've got 0, right? Negative 1 over 0, right? And I don't even like writing that down. It's terrible to look at, right? So we know that this is undefined, right? So, of course, that means what we have here is a divergent sequence. All right, now here's the part where you're going to have a whole bunch of theorems thrown at you. And this is the part where you just kind of take a deep breath and say, okay, this is all the stuff I learned in Calc 1. It's just being put in the language of sequences. All right? The squeeze theorem, right? This is something you should have done in Calc 1. Okay? for us, what we're going to say is if we have a sequence that we are interested in determining the convergence or divergence of, and then we have two other known sequences um, where one of them is all its terms are always smaller than the one we're interested in, and the other one whose terms are always bigger. If these two both converge to the same thing, then the sequence that's squeezed in the middle has to be convergent also. Okay, so that's a really handy little theorem that we'll be able to use. And this doesn't necessarily have to be true from the very beginning, like when n equals 1. It just has to be true at some point, right? So this might be, 11, for example. Like, so when after n is equal to 11, after that, they always have this relationship, then we could say that, yeah, this thing converges. So when those two limits are the same, then that one also has to have that same limit. All right. Anytime the absolute values of all your terms converge to 0, then it's also true that the terms without absolute values, right, positives and negatives both, will converge to 0. And then this theorem basically says this. Maybe I should say it this way. What we just did here, talking about this function here, we really were thinking about it as your typical function where you have an x in here, right? We're analyzing it in that way. This basically gives us permission to do that, right? So if I know that the limit of a function of x is equal to L, then the sequence that uses the same formula is also going to converge to that same limit. And then here is just a big list of things, but basically, let me summarize it like this. All the stuff you could do with limits in Calc 1 with functions, you can do with limits here with sequences, okay? That's all I'm going to say about that. So you can, the limit of things added together, right, is the same as taking the limits separately and then adding those limits as long as both of them are convergent. So all of these properties hold. Basically, you already know them, right? So don't let them intimidate you too much. All right, so I wanted to show an example of the squeeze theorem and how that can work. So here in example 7, we've got this sequence. Just a little reminder here, see how nothing's written, okay? But if nothing's written, I know it starts at 1 and then goes to infinity, right? So if they don't write it, we know that that's where it's going to start at. All right, so does this thing converge? So this cosine raised to the nth power of 1 over n is very distracting, right? It's kind of overwhelming to look at this thing as a whole. Here is where the squeeze theorem can really be helpful. So first of all, let's think about this. When you take the cosine of anything, let's just say the cosine of x, and you raise that cosine to the nth power, right? That's the same as putting the little n right there. Let's think about what is the very biggest that can ever be. Well, the very biggest it could ever be is 1, correct? Because we know that the cosine is never bigger than 1, right? And raising something that is between 0 and 1, or I should say between -1 and 1 even, will never get above 1, right? It can never get bigger than that, right? Just think about things like this. What happens when you take 0.5 to the second power, right? You get 0.25. You get a number that's smaller, right? Squaring things or cubing things or raising things to the fourth. When that number is smaller than 1, gets smaller, not bigger. So I can actually say that this is always less than or equal to 1. And for that matter, because of the fact that the cosine is never smaller than -1, then this could never be any smaller than -1, right? For the same reason over here, negative 0.5 squared. When you do that, you get 0.25, right? Even if you're going to cube it, negative 0.5 to the third power, right? You're going to get negative 0.125. So you're closer to 0, right, when you do that. So the cosine can always be between -1 and 1. Now, there's something more complicated on in here, but guess what? This analysis we just did was just for any old x we want. So the same holds true for this. The cosine to the n of 1 over n always has to be between 1 and -1. All right. So when I am thinking about that divided by n, then of course this always has to be between -1 over n and 1 over n. All right, so now let's think about this. What we've just done is we have squeezed this sequence between two simpler looking sequences, okay? But let's think about -1 over n. We know that it converges, right, to 0, right? The limit as n goes to infinity is 0, and 1 over n converges to 0. So that means that our sequence, right, the cosine to the nth power of 1 over n divided by n converges to 0 by the squeeze theorem. So hopefully that gives you an idea of how we can use that squeeze theorem to answer kind of a complicated looking question. All right, so example 8 here. I want to determine whether this sequence here converges or diverges. Basically, I want to do a couple more examples where we are going to just reintroduce ourselves to some techniques that we are allowed to use when it comes to limits. But again, these are techniques you have done before. All right, so does this converge or diverge? Well, let's take the limit and see. So the limit as n goes to infinity of the natural log 2n plus 1 divided by 3n plus 4. Okay. Now, something that may have kind of slipped your mind from Calc 1 is when you have a continuous function, you are allowed to pull limits inside of that function. You can pull limits in and out, okay? I'll remind you of the formalities of that in the theorem, but I think that you'll basically agree with my doing this. The natural log is definitely a continuous function on its domain. So taking the limit of the natural log of this is the same as the limit of 2n plus 1 over 3n plus 4, and then taking the natural log of that limit, okay? And I look inside here, and I believe that this limit exists, right? It certainly seems like it should. And then what we can do is the same technique we used earlier, which was if I can make n's in the denominator of fractions, then I can much easier, in a much easier fashion, see what's happening when n gets big. So I look down here, and I know I don't want to have any n's in the denominator, so I look at this bottom one. It's to the power of 1. So I'm going to multiply both the top and bottom of that fraction. Oops. sorry about that, by 1 over n. So 1 over n, that's legal as long as I do that on top and bottom. And by the way, just an aside here, if we had an n squared in the denominator here, then I would go ahead and multiply by 1 over n squared. My goal would be to make it so that I can have one of the things in the denominator be just a nice solid number. Okay. All right, so what does that leave us with here? That's going to give us 2 plus 1 over n on top, and then 3 plus 4 over n on bottom. But as we let n go to infinity, that's going to head to 0, that's going to head to 0, and so we have the natural log of 2/3. Okay? And so then that allows us to then say that the sequence converges to the natural log of 2/3. All right, now for an ugly looking one here. So we've got this sequence that we would like to take the limit of. Okay, so we're going to say the limit as n goes to infinity of n squared minus n raised to the 1 over n. So anytime you have variables in the base and the exponent, things get tricky. So on the one hand, we know that the exponent gets closer and closer to 0 as as n gets big. But at the same time that that's happening, the base is getting bigger and bigger and bigger. So the question is, which one of these wins, essentially, right? If the base is getting bigger and bigger and bigger, like if that makes the entire number bigger in the long run, then we're going to be divergent, right? But if the exponent can kind of dominate the action here, then we're going to converge in the long run. So we got to sort all that out. So the best way to sort things like this out are to be able to make it so that they're on a level playing field, maybe, that we don't have this expression up in the exponent anymore. So let's think for a moment. What is the one tool we have that allows us to take exponents and make them exponents no longer? Think about that for just a moment. What is the tool we have? So we took a moment to think about that, but the answer is logarithms, right? We know that if we take the logarithm of an expression like this, that exponent can come down in front. So what we're going to do here is we're going to say, okay, if this limit exists, let's give it a name, L. Okay, so I'm going to start off by saying L equals this. But what I can do, it's kind of similar to the idea that I did in the last problem, is I can go ahead and take the natural log of both sides of this little equation I've made. Right? And then in kind of an opposite move of what I did in the previous problem, right? The previous problem, I had a limit on the outside of a natural log and then I put it inside. Let's go do the reverse. Let's pull the limit out. So we still have the natural log of L is equal to the limit as n goes to infinity of the natural log of n squared minus n to the 1 over n. And then our laws of logarithms allow us to bring that 1 over n down in the front. So this will be the limit as n goes to infinity of 1 over n natural log of n squared minus n. Okay, so does that help, right? Did we make any sense out of anything here? Well, let's see. I guess the first thing that I would have us do is maybe kind of condense this. So I have the natural log of n squared, n squared minus n, all divided by n. Now let's think about what's happening to the top. As n goes to infinity, what's happening to the top? This goes to infinity, right? Even though the natural log is a nice slow growing function, right? It's a slow growing function. It's still a growing function, right? It'll attain any y value we need it to if we let it go out far enough. And then as n goes to infinity, guess what? That goes to infinity. So I want you to think back for a second to Calc 1. What does infinity over infinity make you think of? Hopefully, right? Hopefully at least sounds familiar, but that's an indeterminate form. And when you have an indeterminate form of a limit, what you can do is apply L'Hopital's rule. And so remember, with L'Hopital's rule, what you can do is take the derivative of the top and the bottom, and the limit of the ratio of derivatives will be the same. So we'll say ddn here of the natural log of that. That will be the same as the original limit. Now let's start with the bottom because that looks easy, right? In the bottom there, we just have 1 when you take the derivative. That's a relief, right? Okay, let's think about the top though. On top, I have, remember, the derivative of the natural log of x is 1 over x. So that means the derivative of the natural log of that stuff is 1 over that stuff. But then anytime the stuff in there is complicated, we have to multiply by the derivative of the inside, right? So this is the derivative of n squared minus n. So that means we're taking the limit as n goes to infinity of 2n minus 1 over n squared minus n. Okay, so with that, you have, I guess, a couple of options. If you wanted to, I guess you could take L'Hopital's rule again to make it so that it's just a constant on top and n's on the bottom. And then you'd be able to see that as n goes to infinity, this goes to 0. Or to avoid using L'Hopital's rule again, we really don't need to use it again, right? I can go ahead and just multiply by 1 over n squared on top and bottom, right? That's another way to show what's happening. But even just setting aside all those formalities, I do hope that you would kind of take a moment and look at this and realize if I've got a bigger power on bottom than I do on top, I know that expression ought to be heading toward 0. So I know where this is going, right? I know this is 0. Let's just kind of finish out the formalities. Right? These terms all go to 0, but we have a 1 on the bottom, which is good. So this equals 0. Okay? But before we get too anxious to finish this, let's think about what equals 0. not the original limit, right? I started to get lazy as I went through this problem, but what was it? It was the natural log of L, right? The natural log of our limit was equal to all this stuff. So it's the natural log of L that equals 0, okay? And so the natural log of L equaling 0, right? If I remember the natural log is the log base E of L. And so then rewriting that in exponential form means e to the 0 equals L. So what does that mean? Our limit is 1. Okay. So what we have here is basically a nice balancing act, really. What you have is that the base wants to diverge. The exponential part wants you to go to 0. But they kind of balance each other out, right? Um, because and end up with not 0, but not diverging either, but converging to the number 1. All right. Those last two examples where I was pulling that limit uh, in and out of the natural log function, here's the formal theorem that gives us permission to do that. Um, I'm not going, when you're doing work, when you're doing test questions, I'm not going to be asking you to like refer to this theorem every time you do that. Just do it like I did, right? You notice that the natural log is continuous, so you can pull the limit in and out of that function. And that's what this is giving us permission to do. This is here's a separate idea that's important. One of the things we'll study is the geometric sequence, which has the form r to the n, right? So where r is just some number. Basically, your sequence is going to be convergent if r is between -1 and 1. And you can include 1 in that, but not -1, and divergent for all other values of r. And let's just do a couple examples to understand that this makes sense. If you say 1/2 to the n, you know that that is going to head to 0, right, as n goes to infinity, right? If I do 2 to the n, I know that that's going to infinity as n goes to infinity, right? So it's just this idea that if you have a number smaller than 1 that's being raised to a power, that should be heading to 0. If you have a number bigger than 1, it should be getting bigger and bigger and bigger and bigger. All right, so last idea that we're going to do here, and then we've got one example to kind of go along with it. We need to talk about the idea of a monotonic sequence. Okay, so what do we mean when we say a monotonic sequence? A monotonic sequence is one that is either increasing or decreasing, but not doing both. Okay, so a monotonic sequence is either increasing or it's decreasing. Okay, and then one other definition is what it means for a sequence to be bounded. So if a sequence is bounded above, then that means there's some number m that the sequence can never get bigger than. And if it's bounded below, there's a number little m that the sequence can never get below. All right, so and if you have a sequence that's both bounded above and below, then it is a bounded sequence. Okay, so the reason for these two definitions here is to introduce the monotonic sequence theorem, which is a really nice one. It says that every bounded monotonic sequence is convergent. Okay, so here's what I'll say about that. Sounds like a real fancy theorem, but it actually makes perfect sense. Okay, so let's say here's just your, let's say this is n, 1, 2, 3, and so on, right? If you have capital M up here and you have little m here, And you know that your sequence has to always be in between those two numbers. And in addition to that, you also know that your sequence is monotonic, right? So it's either increasing or decreasing. Let's just say that the sequence starts here, okay? And it's monotonic in the sense that it is always increasing. Then the next dot's got to be above it, and the next dot would have to be the same or above it. And so one or two things is going to happen. Either this dot is going to settle on a particular number, or it's going to keep growing, right? But eventually, as it grows, it's going to run out of room, right? We know it cannot get past this dotted line. And so at the worst, this sequence is going to converge to that top number, capital M, or it will have converged somewhere before that. So that's why every bounded monotonic sequence has to in fact be convergent. So I want to show one example where we can see this happening. It says determine whether the sequence here is a monotonic sequence. If it is, state whether it is increasing or decreasing, and then state whether or not it converges. Okay. So we're looking at this sequence here, all right? And I want to know, is it increasing or is it decreasing? When I start talking about increasing and decreasing, now I hope that also takes you back to Calc 1. So whether a function is increasing or decreasing should make you think of the first derivative, right? So here's what we're going to do. I'm going to think not about the sequence for a moment, but let's think about the function x e to the negative x, right? Because we had one of our theorems earlier said that it was okay to kind of take a sequence and just think about its function, right? Where you kind of replace the n's, which are just 1, 2, 3, 4, with x's, which can be anything. So I'm going to think about this function for a second. Right? So remember, a function is increasing when the first derivative is greater than 0. And it's decreasing when the first derivative is less than 0. So let's go ahead and compute that first derivative. Right? And of course, annoyingly enough, we've got a function that's got the product of two different functions, so we have to use the product rule, right? So the derivative of the first times the second plus the first times the derivative of the second, which would be e to the negative x, but then the chain rule would dictate that I multiply by -1, right? So this will be e to the negative x minus x e to the negative x. And to make this a little nicer to look at, I can always factor out e to the negative x. Okay. So let's think about this for a second. We're interested in when is the derivative positive, when is the derivative negative. Would you agree, first of all, that e to the negative x is always greater than 0, right? Always, right? E to the negative x looks like that, right? It's always above the x-axis, okay? This is less than 0 when? It's less than 0 when x is greater than 1, right? So the moment x gets bigger than 1, this thing is less than 0. So you have something that's always positive times something that's usually negative as soon as x is bigger than 1. So what do we have? So f prime is less than 0 for when x is greater than 1. So, or in other words, f is decreasing for x greater than 1. And so we can take this conclusion that we just made from our function and apply that now to the sequence. So that means this is decreasing, right? It is monotonic. Now, not only is it decreasing, but we actually also could say that it's bounded. And the reason we can say that it's bounded is because you know that this thing is never negative, right? You're plugging in only 1, 2, 3, 4, and so on for n, and exponentials are never going to be negative. So you can say that it's bounded below by, um, by that. And then you also actually know that it's bounded above by 1 times e to the negative 1, right? Plugging 1 into this formula. Why do we know that? Well, because if this thing is always decreasing, then you cannot get bigger than when you started, right? And so the very first term must in fact be the biggest term. So the only important thing was that we bounded it below because we already knew that this had to be the case. So that means the sequence is bounded, right? And because we have both decreasing and bounded, the sequence is convergent. Now, I did want to take a couple of moments before concluding this lesson just to talk about how you can use technology to help you out when it comes to sequences. So in your calculators, if you go to mode, then you can go to what's called sequence mode. So it's down here where you see function. And in previous classes, you've changed to parametric, you've changed to polar, but actually this last one, sequence, is what we're going to use here. So when I hit sequence and I go to my y equals menu, it looks like this. So first off, this first one, when it says n min, that's you telling it where to start. Okay, so let me go back to the some of these earlier sequences that we worked on. Go back to first couple. All right, so this one wanted us to start at n equals 1, so I'd put 1 here. If it asked me to start somewhere else, I'd put that. And then right below that is my formula, right? So here I would put parentheses n plus 5 divided by n. And then if I go to my window, you're going to want to start at 1 and then tell it how far you want it to go. I don't know, maybe let's do the first 25 terms, right, and see what that looks like. You can change your x's. So what's going to happen is your x-axis is going to be your n's, okay? So let's, there's no reason to have negatives here, so let's make that 0. And then I don't know how, we're going out 25, right? So I'll make my x max 25. And you can tell that we're not going to have any negatives in this particular one. And we're going to start off with what? We're going to start off with, what, 6? And it's only going to get smaller from there. So I'm just going to leave the y's just like that. So I'm going to hit graph. And so it literally shows you a sequence, right? Just little dots. And so if you were to graph this before doing any work on it, you'd kind of expect that this is probably going to be a convergent sequence, right? Because it certainly seems like it's converging quite nicely. Now going back to the menu here, let's take a look at example 2. So let's see, down in red here, I'll start that one at 1 as well. And then we'll go, oh, sorry. Actually, that was not what I wanted. I'm going to put 1. 1 right up here, and then for this one, we will do the same thing but with -1 raised to the nth power, and then n plus 5 divided by n. And I'll go ahead and graph that. And so you can see here with the red one, it's alternating, right? And the fact that, yes, it's kind of settling down here a little bit, but it's still alternating. That's why we're getting a divergent sequence there, because it can't settle down. Now, you might want to go out a little further, because you might think, well, maybe it kind of heads towards 0 in the long run. And if it does, then it wouldn't matter if it's bouncing up and down. It would still head to 0. So let's go out a little further. So maybe go to an n max of 100 and an x value of 100 and see what that looks like. And it certainly seems like it hasn't really made much progress between 25 and 100, right? It still seems to be a nice separation between all those red dots. And so I would, at this point with this picture, be thinking, in example 1, I'm anticipating a convergent sequence that converges as probably to the number 1 is what it kind of looks like. And then here I'm expecting a divergent sequence because it can't make up its mind. It can't settle down on any one number. And of course, if we go back here, right? There we go. If we go back here, that's exactly what we found, right? The top one converging to 1 and this one diverging, right? So you can use this to kind of get a sense for what you think is going to happen in a sequence. There's nothing wrong with that at all. Of course, the hard work is doing all your limit work properly, and that's, obviously one of the things I'll be grading for, on a test and that sort of thing. So it's obviously important, but it does help sometimes, especially when you have one that you really don't have much of an idea on. It might give you some ideas. So for example, like this one, you might really have been at a loss. Like, I have no idea if this is going to converge or diverge. So, this would be probably a pretty good one to plug in and see if anything enlightening can be seen here. So n squared minus n raised to the 1 over n. Okay. And I'll hit graph there, and you can see, right, it seems like it's settling down, right? And so at that point, then I would kind of think, okay, so I'm thinking this is going to converge. Now, how do I show it algebraically?